So, all right, let us begin. I welcome you all to this group theory Sangam talk. Our speaker today is Dr. Kashyap Rajeevsarathy, the professor of mathematics at IISER Bhopal, and he is going to speak on liftable mapping class groups of regular cyclic covers.
Thank you, Manoj, and also thank you for inviting me and giving me this opportunity. I appreciate that. So, thank you all for joining us today. And let me get started. Okay, so let me. So I'm going to be talking, as Manoj just mentioned, about liftable mapping class groups of regular cyclic covers. It might look a little bit strange, this title, what it actually means. So let me demystify this a little bit. So let me get through some of the preliminaries. So our setup here is that we have a closed orientable surface of genus G greater than or equal to 0 with B greater than or equal to 0 boundary components and P punctures. So
sorry, Kashyap, we are not able to see your slides.
Oh, really?
At least now I can see. Yeah.
Okay. Shall I keep it this way? Is this fine?
Yes.
Because when I do full screen, there seems to be a problem.
Right. Yeah, this is fine. Maybe then.
Okay. Fine. So is this okay with everybody?
Yes.
Okay. So what I'm trying to say is that so we have a surface of genus G with G greater than or equal to 0 boundary components and B punctures. I'm sorry, genus G, B boundary components and P punctures. Then, so we take the group of self-homeomorphisms on this surface, right? And when we talk about self-homeomorphisms, we talk about orientation-preserving self-homeomorphisms that restrict to identity on the boundary and preserves the set of punctures. So we have a surface of genus G with B boundary components and P punctures, and we look at homeomorphisms that restrict to identity on boundary and preserve the set of punctures. Okay, so that is a topological group. Okay, under the composition.
When you say preserves the punctures, you mean the set of punctures go to set of punctures. It doesn't necessarily fix the punctures, right?
Yes, that's exactly what preserves means. So it maps the set to itself.
Right.
It can pollute within the set. That is allowed.
Sure.
Okay. Now, when I mean, so I take this subgroup, this normal subgroup of this homeomorphism group, which is precisely the path component of the identity. Okay. So so you take, so this is a topological group. You put a topology on it, the compact open topology, and under the topology you have path components, and you take the path component of the identity. Okay. And that is a normal subgroup. This comes from basic theory of topological groups. And so the mapping class group is the homeomorphism group quotient this normal subgroup. Okay, so it's a quotient group. Basically, it's homeomorphism group quotient this normal subgroup. So otherwise, you can also think of this as the path components of the homeomorphism group. So when you take the homeomorphism group and quotient it by the path component of the identity, that is equivalent to taking the group of path components of the homeomorphism group, right? And this is called the mapping class group. And each class here, if you take each coset or whatever, each class comprises of homeomorphisms that are connected to other homeomorphisms by a path. And the path here refers to a homotopy. In this case, it's called an isotopy. So a path in the homeomorphism group is called a homotopy. So it's basically path components of the homeomorphism group. Now, it is well known that if you take the mapping class group of the torus, that is the genus 1 surface, which has no boundary components and no punctures, then that is isomorphic to SL2Z. So this is not very difficult to prove, but this is a very basic fact of mapping class group, and this is something that I want you guys to keep in the back of your mind. And so in otherwise, mod SG is finitely generated and presented for G greater than or equal to 2. That's also well known and well understood. Mod SG is genus G surface is finitely generated and presented for G greater than or equal to 2. It's just a fact. It's nothing. We'll get to some of them. So we know now what a mapping class group is. Now let's move ahead. So in SL2Z, we have a popular normal series, a well-known normal series, which appears in the theory of modular forms. So we have these three congruent subgroups: gamma k, gamma 1k, and gamma 0 of k. So all these groups are, I'm not an expert in all this, but I'm sure most of you are familiar with these congruent subgroups of SL2Z. And the important thing is, if you take gamma 0k quotient gamma 1k, that is isomorphic to the group of units, the multiplicative group of units modulo k. Okay, so you have this normal series in SL2Z. Now I just mentioned that SL2Z is the mapping class group of the genus 1 surface. So the question is, now if you transition and generalize this to the mapping class group of the genus G surface, do we have an analog of this normal series? That is the question mark, right? Or that is the question that we would like to address in this talk. So you have this normal series in SL2Z. Can we generalize it to the mapping class group of the genus G surface? Because mapping class group of the genus 1 surface is SL2Z. Okay, so that's what we are going to address. Any questions?
No, yeah. What is a mapping class group for pair of pant?
What is that?
Mapping class group for
It
pair of pant.
is some. I don't remember the exact thing, but it is you can. I think you can take it, define a map to this. From there to the symmetric group on three letters, and then you can do something, and you will get something of that. I think it is for the sphere it is trivial, right? And for the pair of pans it will be, I think it is S3 if I'm not mistaken. Is that right? I'm trying to think about it.
Okay.
Right. I think it is symmetric group on three letters if I'm not mistaken. Right. So and the thing is that for us, at least, we will be focusing on the closed orientable surface for most of the talk.
So is this group always discrete or something?
Yeah, it will be a discrete subgroup. Yeah,
I see.
it will be a discrete subgroup. A discrete group. Sorry, it will be a discrete group. Yeah. So yeah, that is true, and it's always finitely generated and finitely presented. No problems with that. As long as it is a finite type surface, it's finitely generated and finitely presented. Okay. So, right. So, the question is, does there exist a generalization of this sequence in mod SG? Okay, so we know mod SG, we know this. I'll tell you more about mod SG since many of you might be asking questions about mapping class group. I'll tell you more about mod SG in due course. But the question is, can we generalize this? Okay. Now, let us take P to be a finite sheeted regular branch covering of an hyperbolic surface. Hyperbolic surface, by that I mean a surface with Euler characteristic negative, like genus 2 and higher. Okay, something like that. So you take a finite sheeted covering P from S to X, where S is a hyperbolic surface, and you take the subgroup of all mapping classes that lift under this cover, or which are represented by mapping homeomorphisms that lift under this cover. So mapping class group, we saw it as a quotient group, right? It's a coset group. So each coset is represented by homeomorphism. So you think of that you think of all mapping classes that are represented by homeomorphisms that lift under the cover. Okay. Now, and similarly, you think about the symmetric mapping class group, which is all mapping class group in mod mapping classes in mod S that are represented by homeomorphisms that are fiber preserving under this cover. So when you have a cover from S to X, there is a mapping class group for mod X and a mapping class group for S. You take the subgroup of mod X of mapping classes that can be lifted, and you take the subgroup of the mapping class group of mod S of everything that it is lifted to, of mapping classes which are lifts of mapping classes below. Okay, so these are called symmetric mapping classes, and they are represented by homeomorphisms that are fiber preserving under this cover. And such covers, which are finite sheeted regular branch covers, satisfy something called the Berman-Hilton property. And that is equivalent to saying that this exact sequence exists. Okay, so you have a short exact sequence from S mod PS to L mod P, and the kernel of that is the deck transformation group of this color. Okay. So I forgot to mention that G is the deck transformation group of this color. Okay, or maybe I mentioned it in the first. Yeah, I have mentioned it. So that is the deck transformation. Any questions on this particular slide, because this is very important? Is it clear why these are subgroups? Shall I move ahead? Okay.
Yeah.
Cool. So these are obvious subgroups, and we have the short exact sequence, and this is very essential to us. Now, Berman Hilton, when they studied this property, or how to relate mapping classes across mapping class group across branch covers, the one particular example they examined was this particular example. So you take the hyperelliptic involution, you take the genus 2 surface, and you take an axis through the genus 2 surface that cuts the genus 2 surface at exactly 6 points. The 6 points I have mentioned here. And the quotient of that is the sphere with 6 mark points, or the 6, you can think of it as a sphere with 6 punctures also equivalently. So they studied this particular branch cover, and they showed that for this particular branch cover induced by the action of the hyperelliptic, generated by the hyperelliptic involution, they showed that this has this property. So mod S2, so what this exact sequence says is that the liftable mapping class group under this cover is the entire group mapping class group. So everything lives under this cover. And since everything lives, the symmetric mapping class group is also the whole group on top. So there is a short exact sequence from the mod of S2 to mod S06, whose quotient is basically the deck transformation group of this cover, which is Z mod 2Z. Okay. So they proved, they showed this for this particular cover, and the reason why they did it is that they wanted to derive an explicit presentation for the mapping class group of the genus 2 surface. And using this and using a known presentation for the sphere with 6 punctures and goes into the realms of braid groups and spherical braid groups, what was known at that time, they used that knowledge to derive a presentation for mod S2 by pulling back many of the relations under this. Okay, so this was where this was one of the seminal papers of Berman and Hilton, which was published in the 1970s. And using this, they proved many other things, and this was the central example in that paper. So let us now shift gears and move to a slightly different example. Is this clear to everyone, what this example is all about? Any questions? Okay. Let me move ahead to this next example. So this is an example that we often see on in any first course on algebraic topology. And we see that you can cover a genus G surface by another genus G surface, or another surface of genus G greater than G prime greater than G, by using a finite sheeted cover that is induced by a ZK action. So what you do is, you take this surface on the top and you rotate it by 2 pi by 8 here. So here there are 8 petals to this genus G surface. It's actually, I call it genus GK surface, where K is K times G minus 1 plus 1, and it covers the genus G surface in the bottom. Okay. So what it does is, you take this rotation by 2 pi by 8 and you take the action generated by that, and it will quotient down to this surface, right? And this is, you can get a cover of any genus G greater than or equal to 2 using such a cover, right? And this is a very standard example that you will see in a first course in algebraic topology. And by Berman-Hilton theory again, so such covers, this is a finite branched cover. So it satisfies the Berman-Hilton property. And so because of that, you'll have a short exact sequence of this type. S mod pk is gk to L mod pk is g, and the kernel is Z mod ksn. Okay, so this is the cover that we are going to focus on. This particular cover is the cover that we are going to focus on throughout this talk. And before I tell you how I'm going to generalize that normal series that I mentioned in the beginning, this whatever we are seeing so far, this liftable mapping class groups and this symmetric mapping class groups are going to play a central role in this generalization. Okay, let me actually tell you how we are going to do this. So the first thing we need to know is that the mapping class group has a natural action on the homology, the first homology on the surface of genus G with Z coefficient. So the first homology of the surface of genus G with Z coefficients is Z power 2G, is isomorphic to Z power 2G. And this affords a surjective representation in sp2gz. And if you might wonder why, because there is a alternating bilinear form called the algebraic intersection number that this action preserves. And because of that, it will take you to a symplectic matrix. It will take you to SL2Z, but in particular sp2gz, because it preserves this alternating bilinear form. Okay, so this is the natural action of the mapping class group of homology is given by the symplectic representation. And in the case of G equal to 1, the torus, this is an isomorphism, because all of you know that if you take sp2z, it is the same as SL2z, right? So this is an isomorphism, and the kernel of this map of this representation is called the Torelli group, right? This is well known in algebraic geometry. This is called the Torelli group, and if you instead take the action of the mapping class group on the homology with respect to zk coefficients, that is, if you take mod sg going to sp2gz and then take the mod k map to sp2gzk, then the kernel of this whole map is called the level k congruence subgroup of the mapping class group, and it is denoted by mod sgk. And this is, of course, a finite index subgroup of the mapping class group because of the fact that it is sp2gzk is a finite group. So it's a finite index normal subgroup of the mapping class group. So the important thing to note is that if you take this level k congruence subgroup of the mapping class group, if you take it for the genus 1 surface, this is precisely coincides with your gamma k, the group gamma of k. You can check it yourself, and you can show that gamma of k is nothing but if you take the action of SL2Z, which is the mapping class group of the genus 1 surface, on Z square, ZK square, in fact, ZK square, then it's a kernel of that action. Okay. So any questions on this so far? Can I move ahead?
Yes, sir.
Okay. Yeah. Okay, let me move ahead. So we have the mapping class group, we have the Torelli group, and we also have the level k congruence subgroup of the mapping class group. So at least we know what gamma k is for now. Okay. So let me also think about talk about the generalization of the other groups in that normal series. So this is joint work with Nikita Agarwal, Soumya De, and Neeraj Dhanwani. So let us look at a very simple observation, which comes directly from algebraic topology. So let Ck be the set of all regular k-sheeted covers of the genus G surface, like the ones that I talked about earlier, where you have the flower and you rotate the flower by the petals of the flower by a 2 pi by k action, and you quotient it down to the genus G surface. And this is in one-to-one correspondence with the endomorphisms of pi1 sgk to sg. This comes from covering space theory, because if you have a cover, the fundamental group of the cover embeds into the fundamental group of that surface in the bottom, which it's covering, right? So if you have a cover of some x, so this fundamental group of the cover injects into the fundamental group of x, and so that is the same as epimorphisms from pi1 sg to zk. So with such that if you take p star of pi1 sgk, that is equal to the kernel of phi. So these are all very simple correspondences. And the important thing is, if you take the next, so that is, since zk is a abelian group, you can abelianize both sides. So you're looking at epimorphisms. epimorphisms from pi1sg to zk, which is an abelian group, it is the same as epimorphisms from the abelianization of pi1sg to zk. So abelianization of pi1sg is h1sg, which is the first homology with respect to z coefficients, and then you get this correspondence. And finally, you will see that this is all sets of the form L times V, where V is a primitive vector. So primitive vector of this means that you take some vector of the homology with respect to zk coefficients, which is something of the form zk power 2g. Now in that vector, you take that vector is a class in this, right? It is a modulo k class. Now if that modulo k class is represented by a vector in homology modulo z, where the components have GCD1, then that is called a primitive class. Okay, so if the class zk power 2g if you take an element in zk power 2g, if that is represented by a vector in z power 2g, whose GCD of the GCD of whose components is 1, then that is called a primitive class. Okay. Now the conclusion is, if you take the transitivity of the interesting thing is mod SG acts transitively on the primitive elements of homology modulo zk. The reason is mod SG acts primitively on the simple closed curves, right? And every primitive class in homology is represented by a simple closed curve. So since mod SG acts transitively on the simple closed curves, it acts transitively on the primitive elements, and then obviously by tracing your way back here, it will act transitively on the regular k-sheeted covers. And what you can see is that L mod SG. So hold on here, I don't know how to. Yeah, if you take L mod PKSG, it is the stabilizer of a particular cover, right? So your liftable mapping class group is a stabilizer of a particular cover. And so that is equal to the stabilizer of this collection of vectors. And in particular, you can take your vector to be, instead of V, you can take it to be E1. It doesn't matter. I'm taking it to be the vector E1, where E1 is in ZK. So what we have got here is that the liftable mapping class group is in fact the stabilizer group in mod SG of this collection of vectors, this collection of scaled vectors by this sequence of arguments. Is this clear to everybody? If not, I'll be happy to repeat it. So what we have done is we have made sense of the liftable mapping class group and we have given it a homological criterion. So what we are saying is, if you take the liftable mapping class group, it's nothing but equal to the stabilizer of subgroup of the mapping class group of its action on the collection of these vectors. L times E1, where L contained in ZK cross. Okay, this is very crucial. This interpretation of the liftable mapping class group of that cover that we had fixed is very important. So we'll move ahead. Any questions I would like you, I'd be happy to take them at this point. Okay, I'll go ahead. Now, what have we achieved from all of this? So what we have said is, let me restate what I just said. So you have a liftable mapping class, right? It is equivalent to the stabilizer subgroup of mod SG of this collection of vectors. And immediately once you get this stabilizer, since we know that the representation of mod SG under its action on this homology modulo ZK is given by matrices in sp2g ZK, you will get a sort of a characterization of the matrices that you can expect. So this is psi f is the map, is the representation in sp2gz, and psi k of f is the representation of these mapping classes in sp2g zk, z mod kz. In both of these representations, you get the characterization of the image of an f, which is a liftable mapping class. Right? So we have got a complete characterization of liftable mapping class group. So we know what subgroup it corresponds to, and also in terms of the representation in sp2gz and sp2g z mod kz, we know what it looks like. Okay? So this is the main, the key result that we'll be using for everything that we'll do from here on. So this is very important. Now, we already saw that the mod SGK is the level K congruent subgroup of mod SG, which is basically you take the action of mod SG on the homology on with ZK coefficients, and it's a kernel of that action. And so we immediately get that if for G greater than equal to 2 and K greater than equal to 2, by virtue of this representation or the characterization of the image under these representations, you will see that immediately you will see that the level K congruent subgroup sits inside as a normal subgroup of L mod PKSG. So this is an immediate conclusion. Okay. Now another interesting corollary that comes out of this is that if you take the L mod PKSG and you take that its image under the symplectic representation with Z coefficients, and you also take its image under the symplectic coefficients with representation in the symplectic group with ZK coefficients, then what you will see is that if you take mod SG, the index of L mod PKSG in mod SG, it is the same as sp2gz and this image, and sp2gzk and this image. And by doing some computations, direct computations, we can show that the index of L mod PKSG in mod SG is k to the 2g minus 1 divided by k minus 1. So which is because it's equal to the primitive elements in zk power 2g quotient phi k, where phi k is the Euler-Torsion function. So we can show that the collection of liftable mapping classes under this cover, the index of this subgroup of liftable mapping classes in the mapping class group is precisely k to the 2g minus 1 divided by k minus 1. And everything follows from this theorem. So the minute you have this, everything follows from this. This characterization of liftable mapping classes, from this everything follows. It's just direct computation and just studying the structure of the matrices that appear in the image. In sp2gz and sp2gzk, you get everything. Okay? So this is the first observation we made. So, and here is one more interesting observation. If you take a K-sheeted cover and an L-sheeted cover, right? So let's take L mod PKSG and L mod PLSG, which is the same as L mod PDSG, where D is the LCM of K and L. Okay? So that is also very obvious. You can take again the characterization of the matrices in the image, and then you apply simple K and L and you take this and you will be immediately able to prove it. So basically what we have done is we have characterized all liftable mapping classes by virtue of their representation or the symplectic representation. So once we have that, you can use the symplectic representation judiciously to make all these conclusions, right? Now, another intriguing group that comes here is that you can take U mod SG to be the intersection of all K liftable mapping class groups for K greater than equal to 2, right? The interesting thing about this group is that this group is expected to have this is going to have an infinite index, expected to have an infinite index, and also you see that the Torelli group sits inside this group. Right? So this is not a trivial group. It's a non-trivial group because the Torelli subgroup sits inside this as a normal subgroup. And so the interesting group that comes as a consequence of the groups that we have figured out is this U mod SG. Let me tell you a little bit more about this U mod SG as we progress. Okay? So for now, what we know is that if you take F in mod SG, then we can give a characterization of the symplectic representation of this elements in this group U mod SG, because it is an intersection of all L mod SG groups. So for each L mod SG group is characterized completely by symplectic representation. So you take the intersection of all those symplectic representations and you get a characterization of the representation of this group, and you will get a matrix of this type. So if and only if D2I is 0 for all 1 less than equal to I less than equal to 2g and I not equal to 2 and D2 equal to 1. So we have got several corollaries of this main theorem which gave a symplectic criterion for liftability. And let's move ahead. So let us get now to the generalized normal series. So we introduce a new group now. So what is this new group? We take mod pksge1 to be the stabilizer in mod sg of this vector e1, where vector e1 is the homology vector in h1 sg zk, which is zk power 2g. So you take the vector e1 in zk power 2g and you take the stabilizer, right, of this homology vector, right, in mod sg. And the reason why we are doing this is because of this. Let me quickly tell you. Because we said that liftable mapping class group is the stabilizer of this collection of vectors. So we take this vector e1 up to scaling with elements in zk. So obviously, that's the reason why we are defining this stabilizer. So we are taking stabilizer mod sg e1 to be e1. Stabilizer mod sg of e1, and given an f in mod sg, you can also give a complete symplectic characterization of these this subgroup of the mapping class group, and you can see that just by taking the symplectic representation, you can actually see that it is represented by matrices of this form. Okay, in sp2gz and sp2gzk. So, and why are we interested in this particular group? You will understand now. Okay, so given an f contained in L mod pksg, so anything on whatever, any doubts on whatever I have covered so far? Any doubts before we move ahead into the generalized normal series? Okay, I'll move ahead. So you take an f in L mod pksg and you take its representation in sp2gzk, where e2i is 0. So we know that such a matrix is represented, has this particular structure. We have already seen that earlier in one of the slides. So if you take a representation of this, of a liftable mapping class into the sp2gzk, its matrix is going to have the structure. And since E preserves the symplectic form, so the symplectic form that we use in topology looks like this. This is a little bit different from the symplectic form that you often see in representation theory, but this is the symplectic form that we use, and this J1 is the matrix 0 1 minus 1 0. Okay, so we take the symplectic form, and since it preserves the symplectic form as it's a symplectic matrix, it reduces further to a matrix of this type, E, this matrix. Okay, so what you can see is that, and the important thing to note is that E22 is contained in ZK cross. So you can just see that by just applying the symplectic criterion, that is the fact that symplectic matrices preserve this form. You apply that condition and it reduces any matrix in the image under the symplectic representation of a liftable mapping class takes this form. Okay, and then what further E22 is in ZK cross, that is it's a unit. Then you immediately can consider the obvious epimorphism from this image, which comprises matrices of this form, to ZK cross. What you do, you map each element or each matrix of this form to E22. You map it to the second, the E22th entry, so in ZK cross. So basically, you map this entire matrix to E22, and you can check that this is an epimorphism. Okay, and the kernel of this epimorphism is basically, you can show that it is precisely mod pk sge1. This is the group that we defined earlier. What was mod pk sge1? This is the stabilizer in mod sg of e1. So you can show that the kernel of this epimorphism is precisely matrices that have structure of this type here. So what have we done now? So we know that mod pksge1 now sits as a subgroup, sits inside L mod pksg as a normal subgroup. Okay, so what we have here, so here we are using a group theoretic fact. If you have psi from G to H is a group theoretic epimorphism, and then you have N is a subgroup of G such that N is equal to phi psi inverse of psi of N, then N is normal in G if and only if psi of N is normal in H. Okay, so this is just a simple group theoretic fact, and this leads you, now what you can do is, whatever we proved here, this epimorphism at the level of matrices can be pulled back under the representation to an epimorphism at the level of the mapping class groups, because these are representations of the mapping, these are coming under representations of the mapping class group. You can just pull this back entirely to the level of mapping class groups, and you will see that mod SGK, which we already showed, this is the level K congruent subgroup that sits inside a mod SGE1, which is obvious, we can prove that, and this again sits inside L mod PKSG via that epimorphism, that pulling back that epimorphism. And you can also further show that, since we saw here is that we map E to Z, E to 2, then by virtue of that, you can see that the kernel, the L mod PKSG quotient mod PKSG1 is precisely ZK cross. Okay. Now, so consequently, if you take the index of mod SGE1, that is the stabilizer of this vector E1, right, inside L mod PKSG, that is precisely phi of K, the Euler-Toscan function of K, applied to K, right? So thus we have, so before I do that, is this okay for everyone? Is this okay? Any questions? Hello?
Yeah, it's fine.
Shall I move ahead?
Yeah.
Now, with all this thing that, all these arguments that we have had so far, we put them all together and we achieve this theorem. So for G greater than equal to 1 and K greater than equal to 2, there exists a normal series of L mod PKSG, which looks like this. Okay, so mod SGK here is the level K congruent subgroup of the mapping class group. Mod SPKSG1 is basically it's the you know, the stabilizer of E1, and L mod PKSG is the liftable mapping class group. And if you take L mod PKSG quotient mod PKSG E1, this is ZK cross. Okay. Now, basically, what you can see is that if you take this series and you take its representations that we showed in the symplectic group, every group here is completely characterized by its symplectic representation. So if you take the symplectic representation and scale it down to genus 2 or genus 1 by just taking SL2Z, you will recover back your original series. So what we have got in essence is a generalization of your the normal series in SL2Z. So all of these groups, you can take the symplectic representation and you can bring it down to SL2Z instead of SP, whatever conditions we had in SP2GZ, you bring it down to SL2Z and you will get a series, and that series is exactly coincides with your normal series in SL2Z, right? And topologically also we have interpreted all these groups. So these normal series that you can see here, gamma K is the level K congruent subgroup of the mapping class group of the torus, and gamma 1K is basically the stabilizer of the E1 vector of ZK square, and gamma 0K is the liftable mapping class group of the torus. What is the covering space of the torus? It's the torus itself. So there is a natural K-sheeted cover of the torus to itself. Under that cover, this is the liftable mapping class group. So these groups that that are classically known in number theory and theory of modular forms have a topological interpretation, complete topological interpretation, even in SL2Z. And we have generalized this to mapping class groups. So any questions on this so far? Before I move ahead? Any questions? Okay, so let me me now move ahead. So I also said that I will talk a little bit about generating L mod PKSG. Anupam, how many more minutes do I have?
You have 15 minutes.
Okay, just thank you. All right. So so let us talk about can we, so one natural question that both from a group theoretic perspective and also from a topological perspective is that when you come up with such a group, we know that it's a finite index subgroup, right? So the natural question is, can you derive a generating set, and how difficult or how easy it is. So let me focus on that a little bit. Now, before we do get into that, there is one particular mapping class that we need to have familiarity with, and this is called a Dane twist. Okay, so a Dane twist of an annulus is that you take an annulus and you twist it, keep it on one side intact, and you twist the other side completely by 2 pi, right? So this is called the Dane twist of an annulus, and you can formally you can think of it as a map from S1 cross I to S1 cross I as S comma t going to S e to the 2 pi I t comma t. So that is the map that we are talking about. This map is precisely that. It coils the other thing around this direction. So when it crosses this curve, it completely rotates by 2 pi. And you can think of the same map on a surface in the neighborhood of a curve like this. And again, it twists in the direction of the curve. Okay. And also here, you'll see that this arc gets twisted like this. So this is called a Dane twist on about a curve on a genus D surface. So this is a mapping class. This is definitely a mapping class. So so if you take an isotopic copy of this curve, then you take the Dane twist about that curve. This Dane twist and that Dane twist will be isotopic in the sense that they'll be in the same mapping class. Okay. So this is called the Dane twist. Now, Licorice showed that in 1964, I think, he showed that the mapping class group of the genus G surface is finitely generated by Dane twists. So why do we care about Dane twists? Because these form a finite set of generators of the mapping class group. So you take the genus G surface here, and you take these curves, A1, B1, C1, AG, BG, CG, and you take the Dane twists about all these curves. And you can see that there are 3G minus 1 curves. And these curves, the Dane twists about these curves, generate the mapping class group of the genus G surface. This was shown by Licorice in 1964. In particular, since all of you are curious about SL2Z, this generating set corresponds to this generating set in SL2Z. All of you are familiar with this presentation for SL2Z. You can think of SL2Z as the group generated by A and B, where ABA equal to BAB, and AB power 6 is 1. So this corresponds to the matrix 1, 0, 1, 1 and 1 minus 1, 0, 1. So this is a well-known generating set for SL2Z. And so what generating set I have here is a generalization of this generating set. Okay, for SL2Z. So SL2Z, this is the generating set we are referring to. Okay. Now, any questions on this so far? Okay, so let me move ahead. So we know that this psi-k, which was the representation of the mapping class group in sp2gzk, it induced an isomorphism, okay, of this type, because we saw that these subgroups of the mapping class group were completely characterized, right? They were completely characterized by their symplectic representations, and because of that, this isomorphism came. And it is apparent for each L, the matrix QL, if you take this matrix QL in sp2gzk, which is given by this, okay? So QLij is L if I equal to j equal to 1, and L bar if I equal to j equal to 2, and it's 1 if I equal to j greater than 2, and 0 otherwise. You take this matrix, this represents a coset of this. You can just show that by just direct computation. You can show that if you take the cosets of this group, this represents a coset of this group. Okay. Now you can pull this coset, this representative of this coset, back under the representation and get a corresponding mapping class here that is represented as a product of Dain-Twist under the licorice generators, and this looks precisely like this. TB1 power L bar minus 1, TA1 inverse, and TB1 power L minus 1. Okay, so this represents a coset in this mapping, in this quotient. Okay, so because mod pk SGE1 is a normal subgroup of that, this is a group, quotient group, and in this represents a coset. Okay, so the reason why we want to do this is that you will understand why we want to understand the coset representatives of mod pk SGE1 and L mod pk SGE. Okay, now the immediate thing that you will see is that for g greater than equal to 1 and k greater than equal to 2, the distinct cosets of this are represented by the elements in this precisely. These are the, if you take the cosine representatives of this is precisely represented by elements of this type. That TAB1, TA1, and TB1 are Dain-Twist, okay, of the type that I mentioned earlier. So these are the cosine representatives. Okay. Now, let us get back to generating mod SGE1. So now if we know how to generate mod SGE1, we'll have some idea of how to generate L mod PKSG. So since mod SG, the index of mod SGK in mod SG is sp2g, which is the same as the order of the group sp2g zk, which is less than, which is finite, then SGK be a finite generating set of mod SGK. So what I'm trying to say is, you assume that the level k congruent subgroup of the mapping class group has some generating set, and I'm calling it LG. Okay. Now you might wonder that are such explicit generating sets known? Yes, at least in SL2Z it's known, but for genus G greater than equal to 2, unfortunately such explicit generating sets are not known, right? For the level k congruent subgroups. For specific cases, for level 2 congruent subgroups it's known, but level k it's not known. Okay, now you take sk tilde to be a finite generating set of for mod S1E1, which is gamma 1k in terms of the licorice generators A1 and B1, which I mentioned earlier. Those are these two matrices, 1 1 0 1 and 1 0 minus 1 1. So those two matrices, you take a generating set for gamma 1k, which is known, generating sets for gamma 1k is known, and you take a generating set. Okay. Then you can show that immediately that if for gk greater than equal to 2, this mod pk, the stabilizer group of this vector, is generated by sk tilde union sgk union ta2 up to tag and tb2 up to tbg and tc1 up to tcg minus 1. You can immediately show that these generators, if you take the union of these sets of generators, it will generate the stabilizer group mod SGE1. Okay, and here is one more. So how do we transition from there to the L mod group? So that is what this is about. For that, we have to first understand why this theorem holds true. Okay, so let us think about it. We consider the canonical embedding eta of k from SL2ZK to SP4ZK. So I'm going to give the proof for G equal to 2 because whatever I'm proving here generalizes to the generic case for G greater than equal to 2, but the ideas are still the same. So what you can show is that when you take this particular map, right, if you take this embedding A going to A, O2 and O2 and I2, then we show that if you take an element of psi k mod pks2e1, it is generated by precisely matrices of these types. So what we show is any matrix is in mod pk sg-e1, s2e1 can be written as a product of matrices of this type. This, and this. And this requires a little bit of computation, but it can be shown. So, but you can decompose any matrix in mod pk s2e1 into matrices of this type, and that will immediately show that that this assertion here that mod pk sge1 is in fact the union of these is generated by these elements. Okay. Now, immediately what you get is that as a corollary that you can get is that for gk greater than or equal to 2, L mod pk is generated by sk double prime, sk tilde union sgk union this. So let me also remind you what these things were. Yeah, sk double tilde was this collection of dampers which appeared in as representatives of this coset. These cosets in this, and SGK was a finite generating set for the level K congruent subgroup of the mapping class group, and SK tilde was a finite generating set for gamma 1K. Okay, you put them all together, you get a generating set for L mod PK SG. But of course, this is dependent on a generating set for the level K congruent subgroup, which currently is unknown. But as an immediate consequence of this, you get that for G greater than or equal to 2 and K greater than or equal to 2, right? G greater than or equal to 1 and K greater than or equal to 2, since this U mod, we define it to be the intersection of K greater than or equal to 2 of all liftable mapping classes, you can show that that is generated by this group, SG. Where SG is the generating set for the ternary group of the mapping class group. So this is you take the symplectic representation of the mapping class group under Z coefficients, and you take the kernel of that representation, it is the generating set for that group. So the interesting thing is, for G equal to 2, the ternary group is finitely generated, is not finitely generated. And for G greater than or equal to 2, it is finitely generated. So since the ternary group is finitely generated for G greater than or equal to 3, so is U mod SG. So this proves that the U mod SG group, which is the intersection of all K greater than or equal to 2 L mod PK SG, it is finitely generated for G greater than or equal to 3. And that is precisely what we have shown. And the interesting thing is, for the case when G equal to 2, this question is still open. Okay. So, okay. So, Anupam, do I have more time, or what should I do? Should I continue, or should I stop? What is it?
You can take few minutes if you want. It's okay.
Right. So I just wanted to give one more application, which is more. I wanted to avoid this because since most of the talk has been very group theoretic, there is one small application that I would like to highlight, and then I will end this lecture. And we look at the liftability of periodic elements in the mapping class group. Periodic means finite order torsion in the mapping class group. So William Thurston showed that if you take any mapping class group, this is purely topological, that any mapping class group, any mapping class is represented by a homeomorphism that has exactly one of these three, that is of exactly one of these three types. It is of finite order, or it's reducible. By that it means that it preserves a multi-curve in the surface, or it's pseudo-Lasson, right? That means it preserves a transverse pair of measured foliations on your surface. Suppose if you're not familiar with all this, just ignore it for the time being. And this is called the Nielsen-Thurston classification. And the important thing to note here is that the mapping class group does have torsion. It has elements of finite order. So here is an interesting consequence of whatever we have derived at the level of torsion. So if you have a mapping class of finite order whose corresponding orbifold is positive genus. So when you have a finite action of a mapping class group of finite order, it is represented by a homeomorphism of the same order, and that comes from the Nielsen realization theorem. And you can quotient that surface by that group generated by the homeomorphism, and you get an orbifold. And that if that orbifold has genus, as positive genus, that is with something bigger than a sphere, then F has a conjugate which is in L mod PK SG1. So I don't want to get into the proof. The proof is simple, but I don't want to get into this proof. So this gives an interesting consequence of whatever we have done at the level of torsion. And one more interesting consequence is that So if you take gk greater than or equal to 2, if you take a mapping class of finite order which is irreducible, right? Irreducible means that it doesn't preserve any collection of curves on your surface, then f cannot be in mod pk is J1. That is, it cannot preserve any, it cannot be the stabilizer of homology vector. So I will stop right there. I think I have said enough, and these are some of the references that for this talk. Thank you.
Thank you very much, Kashyap, for this very nice talk.
Right. Thank you. I hope it was easy enough to follow.
Thank
So,
you.
are there questions, comments, suggestions?
I'll be happy to take any questions.
I have a small doubt.
Yeah, please, go ahead.
You said this